Hello, friends. You know that in first lecture, uh, I have derived the equation of motion of a charged particle moving in a uniform magnetic field. And we wrote the Lorentz equations and we have derived the x component of the particle velocity, y component of the particle velocity, and z component of the particle velocity. And you see this equation we have derived. This is the equation which we derived in my previous class. Vx dot is equal to q times Vy, where Vx, you remember, it is an x component of the particle velocity, m is the mass of the particle, and q is the charge. It may be a positive charge, it may have a negative charge, that we will take care. Similarly, we have mvy dot is equal to minus qv vx, and we have found mvz dot is equal to 0, which indicates that the z component of the particle velocity is not at all affected by the uniform magnetic field, and it is moving with a constant velocity, and which we have proved that Vz is equal to Vz0, which I have described last time. And once again, you have this is basically dz by dt is equal to Vz0, and once again you integrate. So we found z component of the particle, right? Z coordinate of the particle is changes linearly with respect to t. Z is equal to Vz0 t plus z0. Well, friends, but you see here, which we have described last time, that since uh, m vx dot, that is d by dt of x, time derivative of x component of the velocity, is not zero, right? That means there is a change in x component of the particle velocity, there is a change in y component of the particle velocity. And I said that since magnetic field is not doing any work on the charged particle, so there is no change in kinetic energy of the particle. Right? Particles are the velocity magnitude remains constant here. So we found that the x and y component of the particle velocity has a simple harmonic variation. There is a variation, and this variation is in harmonic, and they have it as frequency, which we have discussed last time, is basically a ratio of a product of qv to the mass of electron. So this we have described in the previous class, and you all know this factor is very well known, and this is known as cyclotron frequency, or it is known as Larmor frequency. Right? Larmor was a British physicist to honor the scientist. This ratio is known as the Larmor frequency. So you see this Larmor frequency or cyclotron frequency, which I wrote here, QB divided by M. So this once again I rewrite, but I use the magnitude of Q, because you see Q is basically a charged particle. So it may have a negative charge if it is an electron, if it is a positive, and if it is suppose having positive ion is there. So and cyclotron frequency is always positive. So you should write mod Q into V divided by, where V is the applied field. Please remember the characteristic of this. The field is uniform. It is applied along the z direction, right? You may have it may suppose if it is applied along the z direction, then you may consider the plane of your paper or your plane of your monitor or plane of your smartphone is your xy plane, and you may imagine there is an axis which is coming normally outward from the plane of your paper, or plane of your monitor is your z-axis. It may come out, or it may go inward. You may have outward field, you may have an inward field. That both the cases you can consider. You can apply the field along the outward z direction, or you may apply the field along the inward z directions. And now you please remember this particular equation which I write down here. You see, this is the equation which we have already derived, Vx double dot. This we have derived in my first class, and that is cyclotron frequency. And so I'm writing this cyclotron frequency is QB by M is omega C. So you can see this expression is now written as Vx double dot is equal to minus omega C square Vx, where omega C is the frequency, cyclotron frequency. And you know, this is basically a very well-known second order differential equation, and we know the solution of such equations are of this type. So I can write down the solution. These are the general second order differential equation. And it is already we use in quantum mechanics also. Such type of equations are used, and we also use in mechanics also. This equation is widely used, second order differential equation. So the solutions of these equations are of this type. So you see, this equation solution is Vx equal to, I put some constant, you can write some constant C also, but I am writing here Vx0 cos cosine of omega ct plus phi. So we have calculated your x component of the particle. You see, I told you now there is a harmonic variation of like Vx and Vy. So we can, because I mentioned here that x and y component of the particle has a harmonic variation. You can see there is an harmonic variation. X component of particle velocity is changes with a harmonic variation, where phi is the phase angle. And now you see we have this equation. I have already written this equation. Mvx dot equal to qbby. This is also we have derived. I can show you this. These are the three equations which we have derived using equation of motion and comparing the coefficient of unit vector I, j, k. So you know that. So I am taking this equation mvx dot equal to qbby. So this equation you please remember, and now this equation I can write down mvx dot equal to q, so I can make the vy, you see, right? So vy equal to m divided by qb into vx dot, and m by qb, you please remember m by qb, I am writing here plus or minus sign. You please remember, because cyclotron frequency is always positive, but we should consider the sign convention. You know, this is very important. You have an electron, you have an ion. Okay, cyclotron frequency you write positive. So here I writing plus or minus sign. You say Q, because Vy is m over Qb into Vx dot. This Q is the charge carry. You have the charge particle charge. So I can take positive, I can take negative. 1 upon omega c Vx dot. So this is your Vy, and now Vx dot I can take this time derivative of Vx. Okay, so you see, I write down Vy, so Vy is it equal to plus or minus, so there is a plus or minus 1 upon omega c, 1 upon omega is as it is, and now we have a Vx dot, you take a time derivative of this, so Vx 0, and it's a differentiation of cosine is minus sign, so it's minus sign sine omega ct, and d by dt of omega ct plus phi gives you omega c, right? And so there is a minus sign and omega c. This omega c in the numerator and this omega c in the denominator cancels each other. There is a minus sign, and this minus sign, if you have a positive ion, if you have ion, then this positive charge will positive combination with this negative will give you the minus sign. And if you have an electron, is you're right, or you're talking about electron, then this negative charge it combines with this negative charge gives you positive. So here you see I am writing Vy is minus or plus. This plus or minus, minus or plus. Because you see, if it is ion, then positive into negative gives you negative. If it is electron, then the negative into negative gives you positive. So this is very important, and this is for just sign convention. Certain book, it is not mentioned. So you please note down here that is it is Vx0 sine of omega ct plus phi. So we have calculated Vx, we have calculated Vy, and you know Vy is also having a harmonic variation. So Vx is changing, Vy is changing, their function of time as time is changing, but the variation is harmonic with the frequency which we have mentioned. Now once you calculate Vx and once you calculate Vy, Vz we have already calculated. Right, so now from this equation number 2 and this equation number 3, you can see this is Vx, this is Vy. So you take Vx square, okay, and you take a Vy square and take the summation of Vx square plus Vy square. And that is very simple. So you see Vx square is Vx0 square cosine of omega ct plus phi square plus Vy square, the minus become plus is plus again Vx0 square sine square omega ct. So this I am writing here. And if you take Vx0 common, so inside the bracket cos square omega ct plus 5 plus sine square omega ct plus 5, that is 1. So Vx square plus Vy square equal to Vx0 square. So Vx0 is the square root of Vx square plus Vy square. And Vx and Vy, you know, these are basically x component of the particle velocity, and Vy is a y component of the particle velocity, and they are basically perpendicular to the applied magnetic field. This particle velocity component is perpendicular, they are not transverse component and perpendicular component. So here you see I define square root of Vx square plus Vy square is V perpendicular. Look at this. And V perpendicular is the particle velocity of the particle projected in xy plane. You please remember here I said that you see here you have a particle, and this particle experience a force because so there is a change in x component, there is a change in y component, particle z component does not change. But suppose you assume that the initial velocity, that is vz0, v0, initial velocity, that is vz0 is 0. That means you will see that the particle has only two components, that is x component and the y component. In that case, you will see you have Vx component and Vy component. In this case, your particle will always move in xy plane, that is in a transverse plane, and you know it is describing a circular path that we will see by we will derive it that they describe the circular path. So a charged particle when it is subjected in xy plane, I'm okay, yeah, right? And if the magnetic field is along the z direction and the particle is subjected in xy plane, then the particle will describe a circular motion in xy plane. And here which you can see this case, now you can see uh, once you define the Vx0 is basically a square root of Vx square plus Vy square is V perpendicular, and V perpendicular is the velocity of the particle projected in xy plane. Now once you know Vx, once you know Vy, then I can find out x coordinate of the particle velocity. I have Vy, I can find y coordinate of the I'm sorry, I'm not particle value of particle, x coordinate of the particle which is moving in the uniform magnetic field. And then I can find out the y coordinate, right? So you can see here Vx is this is the relation which we have derived Vx0 cosine omega ct plus. Now you take Vx, that is basically displacement, right? Dx by dt, that gives you the x displacement, x coordinate. So x is equal to now dx by dt equal to Vx0 cosine of omega ct. This is known to you, and now you integrate both the sides. So when you integrate both the sides, this gives you x displacement x. X is equal to Vx0, and integration of cos is sine, and you have a omega ct, so it is 1 upon omega c. So Vx0 upon omega c sine omega ct plus 5, plus I put some constant of integration x0, right? X0 is basically the coordinate of the particle, well, particle position at t equal to 0. Once the moment you project the particle at t equal to 0, the its x coordinate of the particle is x0. And similarly, you can see in that case, so now this is basically Vx0, and Vx0 is nothing but V perpendicular. So I write down V perpendicular per divided by omega c, right? And that is sine omega ct plus 5. I can rearrange this equation. I can write x minus x0 is v perpendicular divided by omega c sine of omega ct plus 5. Now, similarly, you have a equation for Vy, which is also we have derived. Vy is also minus plus sine Vx0 sine omega ct plus 5 that we have derived here. Okay, you can see this equation which we have derived here. This is the equation of Vy. Now Vy is nothing but dy by dt, displacement in the y direction. So dy by dt is minus plus Vx0 sine of omega ct plus 5. Integrate with respect to t both the sides. I'm sorry. So once you integrate with respect to t both the sides, you will see this expression. Y, you will get y, and you see the integration of sine is minus cos. So minus, if it is minus, then minus minus plus, and if it is a plus sign here, then you get a minus. So it is plus or minus Vx0 divided by omega c, the cosine of omega ct plus 5, and y0 is a constant of integration. So you can write y minus y0 is this Vx0, the y Vx0 omega c and y0. Once I would like to define this ratio, Vx0 is V perpendicular, and V perpendicular divided by omega c, if you find its dimension, the dimension is the dimension of length, and it is basically known as the Larmor radius. So I mean to say that your particle is describing a circular path in xy plane, and the radius of this circular path is defined as the ratio of V perpendicular divided by omega c. This is known as Larmor radius. So Larmor radius is basically a ratio of V perpendicular divided by omega c. Now omega c is always qb by m. So if you calculate RL, so it will be m V perpendicular divided by qv. So if you know the Larmor radius will be m into V perpendicular divided by qb. So Larmor radius of the particle is directly proportional to the mass of the particle, because you see Larmor radius is directly proportional to mass of the particle. So in the case of ion, the Larmor radius of the ion will be greater than the Larmor radius of electron, because you see omega c is nothing but Eb by m, and that m goes up, so it is mv perpendicular. So Larmor radius of ion is greater than the electron Larmor radius. Similarly, the cyclotron frequency Cyclotron frequency, it is EB divided by M. The cyclotron frequency of electron, cyclotron frequency is inversely proportional to the particle mass. Electron mass is lighter than the mass of ion, and it is very low. So mass of electron is very low. So omega c cyclotron frequency of electron is very much greater than cyclotron frequency of an ion, right? So electron will also gyrate. So I mean to say that the electron and the ion in plasma will describe a circular path. I mean to say that they will gyrate along the field lines. And how many times it is gyrating, they will gyrate. And that the frequency of gyration is described by the Larmor frequency. So the Larmor frequency, or you see, the omega c is EB by n. So the Larmor frequency of electron is greater than Larmor frequency of ion. That is very important. Please note down this. So now once you know this equation, so I can have these two equations, x minus x0 and y minus y0. So I can rewrite this equation. I can combine these equations, and I can write these are the two equations which I got, x minus x0, this equation I'm writing here, y minus y0 I writing, and this factor v perpendicular omega is a Larmor radius, so I write the Larmor radius, and here you please see I write the plus or minus sign to see the sign convention of the charge particle. So here it is mentioned sign convention of the charge particle. Now this is basically, that if you combine this equation, this is basically a equation of circle having radius RL, because equation of circle is x minus h whole square plus y minus k whole square is equal to RL square, where h and k is the center of the circle. So the center of the circle is x0 and y0. So this is known as guiding center. The center of circle, the Larmor radius, is known as the guiding center. The coordinate of the guiding center is x0, y0. So this guiding center, you see, if particle has a velocity along z direction, it is some initial velocity, and then your particle is not only gyrate, but your particle is moving along z direction. Please remember this. If you are projecting your particle in such a manner that the particle possesses a z component to the particle velocity vz, if vz is 0, then particle will describe only circular path in xy plane. But if you are projecting the particle with some initial velocity along z direction, then in addition to x and y component, particle is having z component. So in addition to the circular motion, the particle is also having a linear motion along z direction with a constant velocity. So in that case, your guiding center will move along the z direction. This is we will work out. We will also write some equations of the motion of the guiding center, and you see that the guiding center is x0 and y0. So I said that your electron and ion will gyrate the field line. So omega c is basically decides how fast a particle is gyrating. Because you see omega c is EB by m, and mass of the electron is very small. So the electron will gyrate fast again, and you see ion will gyrate slow. These ions with Larmor frequency small. The Larmor radius, you see the Larmor radius of ion will be greater than the Larmor radius of electron, because mass of the ion is greater than the mass of electron. So here I have mentioned the two pictures. One is the particle which is gyrating along the field directions, you see. Another I have an electron, but you see the direction of gyration is exactly opposite. Here you see that electron is gyrating in a clockwise direction, and here the ion is gyrating in anti-clockwise direction. So that we will see. Here you see I have mentioned the direction of magnetic field. I write the cross here. You see there is no dot, it is cross. So you have to consider that your magnetic field is along the z direction, but it is going into the plane of a paper. It is not coming out from the plane. It's not coming normally outward from the plane of your monitor or plane of your smartphone or your plane of the paper. So here I have mentioned the magnetic field, which is basically coming, which is going into the plane of the paper, right? And in that case, how will you decide your direction? So you have to take your right hand, and once you see this is your right hand, keep your right hand in such a manner that your thumb is pointing along the field direction. So in this way, see this way. I cannot show it, but this way. So if your thumb is this is my thumb, and you have to keep your thumb along the z direction. So the curvature, you can see the curvature of the finger indicate the direction of gyration. So dear friend, please try to understand. I am keeping my thumb along the z directions. Uh, this is my thumb, which is keeping along the z direction. It is going towards the uh, 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 along the z direction means your magnetic field is going into the plane of the paper. So you please try, and you keep your right hand, keep your thumb along the z direction, right, and your z I'm sorry, along the field directions, uh, and your field is going into the plane of a paper. So the curvature of your finger indicates the direction. So here this curvature is clockwise. You can see that curvature is clockwise. It's going like this. So it is, and that's why your electron here, you can see you have the clockwise gyration. And for ion, you have to consider your left hand and keep your left hand in such a manner that your thumb is pointing towards the magnetic field direction, right? Towards the direction of the applied field. Your field is going into the plane of a paper. So you keep your left hand, orient your finger, orient your thumb along the magnetic field direction that is going into the plane of a paper. Then you will see in that case the curvature of your finger indicate the direction of gyration of ion. In that case, you will find that the curvature is towards the anti-clockwise direction. So please remember that electron and ion both are gyrating in the field directions, but the direction of gyration is opposite to each other, and that is why this gyration is the conventional current which you will obtain. You see, because whenever a charge is moving, a moving charge produces a current, a ring of current. So the ring of current, the direction of a ring of current for this electron, and the ring of current which you obtain for ion will be in the same directions. Of course, you see, generally we take a conventional current. A conventional current is always flowing opposite to the flow of electron. So if the electron is moving in anti-clockwise direction, I'm sorry, if the electron is moving in clockwise direction, the conventional current, the ring of current will go in a opposite direction. So here already your positive charge is going in opposite. So the conventional current our same directions. So this, you please remember, this is very important and that is why I write some important things. So let us once again revise that charge particles gyrates about the guiding centers, right, in the plane of a paper when the uniform magnetic field is perpendicular to the plane of paper in the inward directions. Positive ions and electrons moves in a circular path in opposite direction that I have explained. And if your thumb points in the direction of B, right, the positive charge spirals like the fingers of the left hand, and negative charge spirals like those of the right hand, which I have already explained. And now, in addition, you see, I mentioned here that I'm sorry that the drawing is dirty, but please excuse me. You see here, this is your applied field, and your particle is gyrating. This is an electron is moving in clockwise direction. But in addition to uh, the x component and y component, I said that you have a particle velocity is a particle is projected in such a manner that it possesses z component of the particle velocity. And in addition to the motion of gyration, there is a linear motion of particle. So you see, you have, because of the z component of the particle velocity, you will see that the trajectory of a particle is an helical path. So this is the hell. It is like a spring. And now, if Vz is zero, then you have to, like, it will work when you compress the spring. You will have the path that is a circular path which you are obtaining in XY plane. So basically, we have today established that you have the when a particle is moving in a uniform magnetic field, and if it possesses some velocity component along the field direction, then its trajectory is an helical trajectory, and we want to see the features of this helix. We want to find out the pitch of a helix, that is the distance between the two consecutive thread of a helix, I would say. That we will discuss also. And we want to study basic, very important thing, that plasma is behaving like a diamagnetic material in a uniform magnetic field, that we would like to see. It behave like a diamagnetic substance that we want to understand. So I think we will see in lecture number 3, right? I will also upload the assignment for lecture number 1 and 2 very shortly. And once again, I will upload my lecture number 3 to describe the diamagnetic behavior of plasma state, and we want to study the features of the helical path, and we will have some numerical exercise to find out the Larmor radius, Larmor frequency, that we will work out in lecture number 3. I will stop here, my dear friends. Thank you very much for listening me. Okay.